This video was recorded from the International Space Station. Up here it feels incredibly far from Earth. The ISS orbits our planet at an altitude of about 250 miles. That's extremely high. For comparison, commercial airplanes usually fly between 30,000 and 40,000 feet. But when you look at Earth on the scale of the entire planet, the station suddenly doesn't seem that far away at all. The distance from California's west coast to the Nevada state border is roughly the same as the altitude where the station orbits Earth. For context, Earth's diameter is 7,918 miles, so on a planetary scale, the ISS is almost right next to the surface. You may have heard of a place called Point Nemo. It's the point in the Pacific Ocean that is farthest away from any land on the planet. The nearest land from this point is about 1,700 miles away. Almost no shipping routes pass through this area, and aircraft try to avoid flying over it unless absolutely necessary. Sometimes people say that if you somehow ended up there, the closest people to you would not be on Earth, but up on the International Space Station. And knowing how close the station actually orbits, you can see that this is not far from the truth. The ISS really can be closer to you than any land on Earth. So, if the station is still this close to Earth, and gravity up here is nearly as strong as on the surface, why doesn't it fall back to Earth? But actually, it is falling. The station is constantly being pulled toward Earth by gravity, just like everything else. The reason it doesn't crash is not because gravity is weak, but because the station is moving sideways incredibly fast at the same time. So instead of falling straight down, it keeps missing the Earth as it falls. And for that to be possible, the station has to move at an enormous speed. In reality, it's traveling at 17,398 miles per hour. This is known as orbital velocity, the minimum speed required to stay in orbit around Earth. If it were moving any slower, gravity would gradually pull it down, and the station would eventually fall back to Earth. The ISS circles Earth once every 90 minutes. That means the crew witnesses around 16 sunrises and sunsets every single day. When you watch footage from the station, it often looks like it's just calmly drifting above Earth. But that calm feeling is mostly an illusion of scale. Imagine the station flying just overhead. This is how it would look like. Interestingly, rockets work in a very similar way. At first, they rise almost straight up, but very quickly, they begin to tilt and accelerate sideways, building up that same orbital velocity. As the rocket continues to accelerate, it can reach what's known as escape velocity. At that point, it has enough speed to break free from Earth's gravity and continue out into deep space. What allows objects to maintain such high speeds is the fact that up here, there's almost nothing slowing them down. At this altitude, the air doesn't disappear, but it becomes extremely thin. The particles are still there, but they're so far apart that there's almost no drag. And that's what makes stable orbit possible. To understand this better, let's look at how Earth's atmosphere is structured. The lowest layer is the troposphere, which extends up to 7.5 miles. This is where we live, and where all weather takes place: clouds, rain, snow, and storms. Commercial airplanes often fly near the top of this layer, above most of the weather, where the air is thinner, reducing drag and making flight more efficient. Above that is the stratosphere, which extends up to 31 miles. Then comes the mesosphere, reaching up to 53 miles. Above that is the thermosphere, stretching hundreds of miles into space. This is the region where the International Space Station orbits, at an altitude of 250 miles. But the edge of space isn't here. It actually begins much lower, at just 62 miles above Earth, at what is known as the Kármán line. So yes, the station and everything inside it is in a constant state of falling around the planet. And that includes the astronauts themselves. They're not floating because gravity is gone. They're floating because they're in continuous free fall. And this is where things start to feel very different from life on Earth. The first thing that really changes up here is the human body. Without gravity compressing the spine, the vertebrae slowly spread apart. Astronauts can grow by about 1 to 2 inches in space, but once they return to Earth, they gradually shrink back to their normal height. Muscles are another major issue. On Earth, simply standing and walking constantly put load on our muscles. In orbit, the body no longer needs to support its own weight, so muscles weaken and shrink much faster than they would on Earth. That's why astronauts exercise for about 2 hours every single day, using special machines that simulate resistance. Without that training, they could lose enough strength that walking after landing would be difficult. But even with regular exercise, many astronauts feel weak or dizzy when they first return to Earth. Some need days, sometimes weeks before their bodies fully readjust. The usual downward direction simply disappears. If you let go of something, it doesn't fall. It just stays where you left it, until it slowly drifts into something else. That's why almost everything on the station is secured with Velcro, straps, or clips. Astronauts get so used to this that after returning to Earth, they sometimes randomly let go of things, forgetting that gravity is back. Liquids behave very differently too. Without gravity, water doesn't pour or drip. Instead, it forms floating spheres, held together by surface tension. That's why astronauts drink in different ways, sometimes from sealed drink bags using a straw-style adapter, and sometimes by guiding small floating blobs straight to the mouth. And even tears follow the same rules as water. In microgravity, they don't run down your face, they can collect into little floating blobs until you wipe them away. Food has to be carefully designed. Nothing that crumbles is allowed on the station. Tiny crumbs can float into vents, get into equipment, or be inhaled. So most meals come in sealed packages or in soft pieces that won't break apart. Basic hygiene also changes. Astronauts don't take normal showers. Instead, they use wet towels and special no-rinse soap. They wash their hair with a shampoo that doesn't require rinsing. You apply it, wipe it off with a towel, and that's it. And it's not just liquids that behave differently. Air does too. On Earth, warm air rises and cold air sinks, so air circulates naturally. But in microgravity, that circulation simply doesn't happen. Without constant ventilation, the carbon dioxide we breathe out could build up around a person's head. That's why the station relies on powerful fans to continuously move and filter the air. The toilet is also very different from anything on Earth. It works more like a vacuum system than traditional plumbing. Airflow is used to guide waste into separate containers. Solid waste is stored and later sent back into the atmosphere to burn up during re-entry. Liquids are collected separately, and this is where the system becomes extremely efficient. Urine, sweat, and even moisture from breathing are recycled into clean drinking water. The water passes through multiple stages of filtration and purification until it's safe to drink again. Because delivering water to space is extraordinarily expensive, recycling isn't just helpful, it's essential. And despite all of this, the astronauts are working. The ISS is a fully functioning research laboratory in orbit. Every day, crew members conduct experiments that simply can't be done on Earth. They study everything from plant growth and muscle loss to advanced materials, physics, and long-term human health in space. And sometimes, they even step outside. During spacewalks, known as EVAS, astronauts leave the safety of the station to install new equipment, repair systems, or upgrade solar arrays. floating above Earth at nearly 17,500 miles per hour, attached only by a tether. They work in complete silence with nothing but the planet below them. So life on the ISS isn't just about adapting to weightlessness. It's about performing complex scientific work in one of the most extreme environments humans have ever operated in. But even in orbit, the crew still has to rest. Sleeping in microgravity looks very different from anything we're used to on Earth. There are no beds. Astronauts zip themselves into sleeping bags that are attached to the wall, or sometimes even the ceiling. In space, those directions don't really matter. Without gravity pulling on the body, there's no pressure on your back, no weight on your shoulders. Some astronauts say it feels like sleeping while floating in midair, because that's exactly what they're doing. And time itself feels unusual up there. As we already know, the station circles Earth every 90 minutes, which means the crew sees a sunrise 16 times a day. But they don't live by the sun. Instead, the ISS follows a strict schedule based on Coordinated Universal Time, UTC. Daily routines, work, exercise, meals, and sleep are carefully planned on that clock. Over time, astronauts rely less on what they see outside and more on their internal sense of rhythm to maintain a normal day-night cycle. Because without structure, with light and darkness constantly alternating, the human body can easily lose track of time. But being in orbit doesn't just change how you live and work. It also means dealing with dangers that simply don't exist on Earth. One of the biggest threats up here is space debris, tiny fragments from old satellites, broken equipment, and even small flakes of paint, all circling the planet at extreme speeds. And the truly dangerous part is that speed. Most debris in low Earth orbit travels at around 17,000 miles per hour. At those velocities, even something as small as a screw can puncture metal. That's why the station is wrapped in special protective shielding designed to absorb and fragment small impacts before they reach the main structure. But larger objects can't be shielded against. Those have to be avoided. Teams on the ground constantly track thousands of pieces of debris. If something is predicted to pass too close, the station performs a debris avoidance maneuver, a small engine burn that slightly shifts its orbit. These maneuvers aren't frequent, but they are absolutely critical. And debris isn't the only risk. There are also micrometeoroids, natural particles left behind by comets and asteroids. They're often smaller than debris, but can move even faster, and they can strike from any direction. There's no thick atmosphere up here to burn them up before impact, so the station must always be ready for something it never sees coming. And that leads to another question. How do you control something this large in space when there's nothing to push against? Most of the time, the station relies on control moment gyroscopes, or CMGs. These are enormous spinning wheels mounted inside the station's structure. Each wheel is already rotating at high speed. When the station tilts the axis of one of these wheels, the conservation of angular momentum causes the entire station to rotate in the opposite direction. It's the same physical principle you see if someone sits on a spinning chair holding a bicycle wheel. Tilt the wheel and the person begins to rotate. The ISS does the same thing, just on a much larger scale. Each gyroscope weighs about 600 pounds, and there are 4 of them working together to control the station's orientation. They allow the station to slowly rotate to keep its solar panels facing the sun and its antennas pointed toward Earth, all without burning fuel. Interestingly, the same physics principle shows up somewhere much closer to home. Cats are able to land on their feet using conservation of angular momentum. They twist different parts of their body in opposite directions, allowing them to reorient midair without pushing against anything. The ISS does something similar, just with spinning wheels instead of muscles and a tail. And all of this precision control is necessary because the ISS is not small. From end to end, the station measures about 357 feet across. That's roughly the length of a football field. its solar arrays extend even farther, spanning about 240 feet from tip to tip. Those panels generate enough electricity to power the entire station continuously. And all of this massive, delicate structure, is orbiting Earth at roughly 17,500 miles per hour. Which raises an even bigger question. How do you build something this large in the vacuum of space? The ISS wasn't launched in one piece. It was assembled module by module over more than a decade. Each section was launched separately and then carefully docked in orbit. Astronauts performed spacewalks to connect cables, cooling systems, power lines, and structural components by hand. What we see today is the result of dozens of launches, hundreds of hours of spacewalks, and cooperation between multiple nations. It isn't just a laboratory in orbit. It's one of the most complex machines humans have ever built and kept alive beyond Earth.